Welcome everyone. Today we are diving deep into something that really separates good network engineers from great architects. Understanding layer 2 design from first principles. I'm really excited about this one.
Me too. And we're not just talking about protocols and commands, right? This is about thinking architecturally.
Exactly. So let's start with something fundamental that a lot of people overlook. Before we even talk about redundancy or convergence tuning, we need to understand what Ethernet actually does. And here's the thing, Ethernet floods. It's designed to flood.
What do you mean by that?
Well, think about it. Unknown unicast traffic, it gets flooded. Broadcasts, flooded. Multicast without proper control, also flooded. And this isn't a bug or a flaw. It's completely deterministic behavior. It's just how Ethernet works.
So when we create a VLAN, we're really creating what?
You're creating three things at once: a broadcast domain, a flooding domain, and what I call a shared fate domain. This is where architectural thinking kicks in. Here's the key question you need to ask yourself. If a broadcast storm happens, how many endpoints get impacted?
That sounds like it could vary a lot depending on the design.
Absolutely. If your answer is only the devices in this wiring closet, then you've got controlled blast radius. But if your answer is the entire campus, well, that's structural risk built into your design. So the next question becomes, why are these endpoints even in the same VLAN?
What would be valid reasons for that?
There are really only three valid technical reasons. One, they actually need same subnet adjacency. Two, you need mobility without changing IP addresses. Or three, the application genuinely requires layer 2 adjacency. But you know what I see all the time? People say it was easier, or it's always been this way, or it reduced configuration steps. Those are not architectural answers.
So what should an architect do instead?
Simple principle. If adjacency isn't explicitly required, enforce a layer 3 boundary. Let me give you a scale example. Imagine you've got 2000 endpoints and they are all ARPing every few minutes. Now picture what happens during MAC table flush events. You get massive flooding spikes. The bottom line, your VLAN size literally defines your blast radius, and that blast radius needs to align with what your business can tolerate.
That makes sense. Now, what about spanning tree? I know it's fundamental for loop prevention.
Here's the thing people forget. Ethernet has no time to live mechanism like IP does. So loops are absolutely fatal. Spanning tree exists to prevent infinite forwarding, but there's a trade-off that's not immediately obvious.
What's the trade-off?
We install redundant links for resilience, and then we intentionally block them. But the real hidden cost isn't the blocked links. It's the shared convergence scope. If a single access uplink fails, that topology recalculation propagates across your entire layer 2 domain.
Can you give us a real-world scenario where this matters?
Sure, imagine a hospital with telemetry systems monitoring patients. One access link fails, spanning tree recalculates, MAC tables flush, and you get temporary flooding increase. Medical monitoring sessions have to retry. Now ask yourself, is 2 to 5 seconds of disruption acceptable in that environment?
Probably not.
Exactly. If your SLA demands sub-second recovery, you've got two choices. Reduce your layer 2 domain size or remove spanning tree from the access layer entirely. This is actually why routed access exists, not because it's trendy, but for convergence containment. Remember this principle. The size of your STP domain equals the size of your convergence blast radius.
Now let's talk about VLAN strategy. I imagine a lot of organizations struggle with this.
Oh, absolutely. VLANs are powerful segmentation tools. Security zoning, policy enforcement, broadcast containment. But here's what people don't think about. Every VLAN you add introduces gateway redundancy configuration, STP participation, trunk tagging, IP addressing overhead, and operational complexity.
So there's a cost to each VLAN beyond just the configuration.
Exactly. The question you need to ask is, does this VLAN reduce risk or does it actually increase complexity? I've seen enterprises with 150 VLANs trunked everywhere, created because of organizational structure rather than technical necessity. What happens when you need to troubleshoot? Cognitive load goes through the roof, misconfiguration probability increases, STP complexity explodes.
So, what's the architectural answer?
Segmentation has to map to risk boundaries, not org charts. And always ask, can this separation be enforced at layer 3 instead? Because layer 3 reduces shared fate, while layer 2 extends it. Only extend layer 2 when adjacency is truly mandatory. Otherwise, entropy grows faster than your segmentation benefits.
What about broadcast and unknown unicast traffic at scale?
This is where architectural thinking becomes really quantitative. Broadcast, unknown unicast, and multicast scale with endpoint density. If each host is generating periodic ARP requests, DHCP renewals, service discovery, and you multiply that by thousands of endpoints, it adds up fast.
What happens during failure scenarios?
Let me paint you a picture. Manufacturing campus with PLC controllers. Someone deployed a flat VLAN across multiple production halls. One switch has an instability event, causes flooding, controllers experience latency spikes, and production briefly halts. Was bandwidth exhausted? Nope. The shared fate domain was just too large.
How would you fix that?
Segment VLANs per production hall, route between the halls, limit pump propagation. Here's the principle. When instability appears, shrink broadcast domains first. Containment creates resilience.
Let's talk about uplink strategy. EtherChannel is pretty common, right?
Yeah, and it's great for throughput. Four 10 gig links become a 40 gig logical link. But here's the architectural question. If that port channel fails, how much capacity disappears at once? All of it. Bundling increases performance, but it also increases what I call failure step size.
Are there other risks with link aggregation?
Definitely. If it's misconfigured, a loop can propagate across all members instantly. And consider hashing. If traffic distribution is uneven, one member link might microburst while others are idle. Application performance degrades even though you've got plenty of aggregate capacity.
What's your recommendation?
Monitor per member utilization. Align your hashing algorithms. Avoid platform asymmetry. The principle is simple. Performance gain must not increase unpredictability. Aggregation concentrates both capacity and consequence.
Now, convergence engineering. This sounds important.
It's critical. Convergence is not luck, it's engineered. It's the sum of failure detection time, protocol reaction time, topology recalculation scope, and fib update time. The key question is, where is convergence happening? Across your entire campus or just one switch?
Do you have an example of this going wrong?
Trading firm. STP recalculation caused 8 seconds of outage. Revenue impact was significant. They redesigned with routed access, link state routing between layers, eliminated STP dependency in access. Result: convergence under 300 milliseconds. The insight here is, don't try to tune convergence if you can localize it instead. Determinism beats optimization every time.
What about gateway redundancy? HSRP, VRRP, GLBP?
Great question. HSRP and VRRP use a single active gateway. When it fails, the entire VLAN is impacted until the transition completes. GLBP is different. Multiple active forwarders, so failure only impacts a subset of hosts. The question becomes, is total outage acceptable for this VLAN?
I imagine that depends on the use case.
Exactly. Dormitory network, Total outage for a few seconds? Probably fine. Trading floor? Absolutely not acceptable. If business requires continuity under partial infrastructure failure, design for partial degradation. GLBP increases complexity but reduces failure scope. The rule is failure behavior must match business tolerance.
Let's talk about route bridge placement. Why does this matter?
Route placement defines logical forwarding paths. Here's the key question. Where does 80% of your traffic actually flow? Usually it's north-south, from access to distribution to core. If you place the route at access, traffic hairpins across distribution unnecessarily. Latency increases, bandwidth is wasted.
Has this caused problems in real networks?
Oh yeah, I've seen unified communications environments where RTP streams traversed suboptimal paths because of access route misplacement. Mean opinion score degraded, users complained about voice quality. The fix? Primary and secondary route at the distribution pair. Traffic aligned with hierarchy. STP is actually traffic engineering, not just default config.
What about protecting the edge from human error?
This is so important. Humans create loops accidentally all the time. Imagine a contractor connects two wall ports together. What happens? If PPDU guard is absent, the storm propagates. If port security is absent, MAC duplication spreads throughout your network.
How do you design for this?
Assume mistakes will happen and design automatic containment. Every edge template must include port fast, BPDU guard, root guard, and port security. Your architecture must defend itself without human intervention.
Traffic matrix modeling. What should architects be looking at?
Design based on observed patterns. If 80% of your traffic is north-south, your design must optimize for north-south. Ask yourself, are interdistribution links carrying more traffic than uplinks to core? If yes, your design is misaligned. Architecture must reflect dominant flow, not just symmetrical diagrams that look pretty.
VTP is something I hear mixed opinions about.
For good reason. VTP server mode centralizes the VLAN database, which seems convenient. But what's the blast radius of a revision override? The entire domain. One error and dozens of switches lose their VLANs. I've seen healthcare mergers where production VLANs got erased during integration because of VTP.
What's the solution?
Set VTP to transparent or disable it entirely. Use automation for provisioning instead. Contain the blast radius to one switch. Same with TTP. Why allow trunk negotiation delay if deterministic trunking is possible? There's no good reason. Explicit configuration removes timing variability. Governance reduces fragility.
The big debate. Layer 2 versus Layer 3 access. How do you decide?
It's a strategic fork. What matters more to your business, mobility or convergence? Looped Layer 2 gives you native same subnet mobility but larger failure domains. Routed access gives you tiny Layer 2 domains and fast convergence, but you need overlay for extension.
So context matters.
Absolutely. University campus prioritizing student mobility, looped Layer 2 is justified. Enterprise headquarters prioritizing microsegmentation and sub-second failover, routed access is the right choice. Choose based on dominant business requirement, not ideology or what's trendy.
HSRP versus GLBP. What about HSRP versus GLBP at the internet edge specifically?
Great distinction. At the internet edge, asymmetry is usually not acceptable. GLBP can introduce asymmetric return paths, which causes firewall state to drop. HSRP enforces symmetry. At boundaries, predictability outweighs utilization efficiency. Your internal campus might tolerate some load polarization, but the perimeter cannot.
Any other examples of alignment issues?
Manufacturing control systems experiencing jitter due to access route misalignment. The question is traffic following physical hierarchy? If not, realign the route to distribution. Traffic matrix must align with logical topology.
When designing for failure, what's the key trade-off?
Is degraded service better than total outage? If yes, use GLBP or distribute gateway roles. If no, simplify with active standby. Architectural thinking always compares complexity cost versus failure tolerance gain.
What about port security for automated enforcement?
Here's a scenario. What if a non-intelligent switch creates a loop without sending BPTUs? BPTU guard fails to catch it. But port security detects MAC duplication and triggers automatic shutdown. The principle is protection must not depend on protocol cooperation. Human error is predictable, so design must assume it.
Is there ever a case where VLAN everywhere is still the right choice?
Yes, if seamless mobility is business critical and your domain size is bounded, looped layer 2 remains valid. But if scale, segmentation, and convergence dominate your requirements, then routed access with overlay is preferred. Architectural maturity means rejecting dogma. Context defines correctness.
Let's wrap up with the architect mindset. What's the key takeaway?
At CCDE level, you never ask, what protocol should I use? You ask, how large is the failure domain? How fast is convergence? What's the blast radius? Is recovery deterministic? Does this design scale for 5 years? Does it reduce operational entropy?
So it's about structured reasoning?
Exactly. Every design decision must be defensible in terms of risk containment, business alignment, operational predictability, and failure scope control. Design is not about configuration commands. It's about consequence modeling. Think in blast radius. Think in convergence domain. Think in shared fate. Then design deliberately.
This has been an incredible deep dive. Thank you for breaking down these architectural principles.
My pleasure. Remember, architecture is about thinking through consequences before they happen. Until next time, design deliberately.
Thanks for joining us, everyone.